industrial AM applications. My name's Erin Brodie, and my background is I have a PhD in 3D printing of titanium using mainly laser powder bed fusion techniques. And now I'm managing at Monash University the 3D printing lab, so the Woodside FutureLab. We do a lot of different AM applications, from energy to biomedical to pretty much across everything, both metals, both polymers. No ceramics yet, though we do have one ceramic company that was a spin out of the lab. However, today I would like to introduce my fantastic panel members who are going to talk about some of the different materials in the AM industry. We have Trish Pollock here, who is from AML 3D. She's the marketing specialist over there, and they specialize in metal wire arc AM.
Yep. Hello, everybody.
Thanks, Trish. I'd also like to introduce Shilpi Sen, who is the CEO and co-founder of Prayasta, and they specialize in additive manufacturing of silicon implants and have developed their own very new technology to actually be able to do that.
Hi.
Hi, Shilpi. Next, I'd like to introduce Seema Negi, who is a PhD candidate in IIT Bombay, and she specializes in ceramics. So she's going to be our ceramic material expert for the panel today.
Hello, everyone.
Hi. And then finally, there's Dina Bayoumy, and she is a mechanical engineer at the Monash Center for Additive Manufacturing. And she also specializes in laser powder bed fusion, however, in aluminium alloys and also alloy design for laser powder bed fusion. So please feel free to ask questions in the Q&A box throughout the session. I will keep an eye on that and ask any of the questions that you may have to the panel. From our end, we're probably going to try and section it a little bit into materials categories. So we're going to start with ceramics with Seema, then we'll move on to polymers with Shilpi, and we'll end up with the metals at the end with Trish and Dina. So without much further ado, Seema, would you like to give us an introduction into ceramics 3D printing, talk about a little bit about the difficulties and why and how digital light processing of ceramics actually works? Thanks, Seema. And you're on mute. Yeah, all good.
Everyone, so for ceramic, if you might know that ceramic itself is the material which is different from polymer and metal, and if you see conventional processes of manufacturing, that is also difficult for ceramic because of its properties. It's a very brittle kind of a material, and the forming of the ceramic is very difficult if you see the conventional processes. Then come to the additive manufacturing of ceramic, you will see that the process starts with all the pre-planning, like the CAD modeling and the process planning, and after that we do the forming from different kind of a 3D printing processes which are available in the market. But if you see typically for technical ceramic material, then the wet photopolymerization based process is the best process because it provides you very precise and very complex shape. So this process has been shown tremendous success in industry. So that's why there are so many systems also which are available. So once we get the shape of the material, after that there are the necessary process like debinding, you can say, or post thermal process, sintering also, which we need to do to densify the ceramic material after shaping that, and then in that way we get the final shape of the ceramic material. So for shaping the ceramic material, there are several processes available. If you see the ASTM classification of all the AM process, and these are the 7 processes are there, and every process has been used for ceramic manufacturing, but out of this, wet photopolymerization has been successfully done for technical ceramic. So in this particular process, we are working with digital light processing, DLP, where we use projection technology for printing the photosensitive resin. And here For projection technology, we use the DMD, which is called as digital micro mirror device, and it is a Texas technology. So for all the system, whatever the in the market available, they use DMD as a image technology, and in that way we produce the parts. So there, the main, if you see the raw material, it is like a photosensitive resin, where we have to mix all the monomers uh, and photo initiator with different kind of ceramic which you want to print, and then we have to make the photosensitive slurry. So here, when we make the slurry, the main point is its viscosity, that it should be perfectly flowable on the vat, so that the build platform can come, and the light get projected on the vat which contains this particular slurry, and then it get printed on the build platform. So the viscosity is the very important part of this slurry. After that, its curing should be fast enough, so the process should not delay. So these are the two property which we need to take care while we are developing the slurry. Yeah.
Awesome. Thanks, Seema. What sort of ceramics have you printed to date? What different types of materials, and what are some of the pros and cons of those different materials that you've been printing with?
So yeah, so we actually started with alumina, which is a very basic ceramic material, because it's refractive. So yeah, when we print, so I should start with this. So when we print the ceramic slurry, the main point is its refractive index. So the refractive index of ceramic with respect to refractive index of resin, it should not be very much different. Otherwise, that variation creates the scattering of the light, and because of which the printing is very difficult. So if you see all the resin, the refractive index is all about like 1.45 or 1.46. So like refractive index of all the resin is same. So the refractive index of ceramic is different. For alumina it is different, for zirconia it is different. So when it is diffractive index is large, so scattering happens. So like the material like zirconia, or you can see non-oxide materials, so it's very difficult because all the light which pass on the resin, it get scattered, so we do not get the fine feature size. So that problems happens apart from silica and alumina. So we so far we have printed alumina, silica also, some zirconia parts also, but with zirconia we get lots of problem because its refractive index is high. So yeah, and we are looking right now we are also looking for glass to print in the future.
Fantastic. Also, from what I understand, with developing the slurries and the resins, you're suspending the ceramic particles in the resin
Right.
itself. What sort of sizes are you looking at in the ceramic particles, and how does that affect the resolution of your final prints?
Yeah, so that is also one more important thing when we make the slurry, because it should be suspended inside all the resin system. So there the stability of ceramic matters a lot, like all the colloidal signs play the role. So we have to I mean, the very important thing that what kind of a dispersant we are using, because we have to provide like steric kind of a stability over there. Otherwise all the ceramic will settle down, and then when we will print the part, then you will see the variation in the material property. Yeah, so definitely we are looking on like colloidal of the ceramic. So
And
that
there's
is
just a
also.
question that's popped up in the QA. What kind of resins are you using for the photopolymerization? Are you using commercially available ones, developing your own from basic
So
monomers and
we are
photoimaging
using both.
resins?
We are using both. There are in the market. There are several commercially available resin system, but we are developing our own also. It is basically acrylate based resin, and a monofunctional acrylate based system. So we are developing our own also, and we have also used commercially available, like there are several Algo or Anycube they are providing some kind of commercially available resins. Yeah.
You mentioned that the viscosity is a very important part of the resin.
Yeah, there is
When you're
viscosity is
developing your own, are you...
especially after mixing the ceramic with it. I mean,
Yeah.
in the market you will get the photosensitive resin, but not a ceramic slurry. So I have to make the ceramic slurry also. And when you increase the volume percentage of ceramic, then viscosity is very high. So that part I have to take care.
Yep. I guess my other final question, coming from a metals background, obviously you do have that slurry, and then afterwards you have to, I assume, bake the part to burn away this binder. How does that burning away really affect the resolution of your part and its structural integrity as well?
Yeah, so it's very important, because see, the when we do the photopolymerization, all these photosensitive resin get 3D there will be kind of a 3D network between these organic system, right? So when we do the debinding, so it should be very slow enough, and it goes up to like 600 degrees centigrade. All the kind of acrylic resin get away till 600 degrees centigrade, and it should be slow enough. Otherwise what will happen, all the gases which get developed during the heating, it will explode the material, and because of which all the cracks will develop. And when cracks happens, then definitely the surface finish will go down, right? So in that way the surface finish and resolution happen means get deteriorate because of the bad debinding. Yeah. And the integrity definitely matters, because if one single crack will happen during the debinding, it will propagate while we will do the sintering, so all part will damage. Yeah.
Yeah. Thank you, Seema, so much. I'm aware of time and that we're going to have to move on to our other materials classes, but if there are any ceramics questions, feel free to pop them up and I will circle back to Seema at the end, hopefully when we have some time. Thank you very much. Next, I'm going to move on to Shilpi and her fantastic silicone work. She's got a small video that I'm going to play of their process, and she's just going to speak to that and give you a little bit of an introduction into their technique before we move on to further panel questions. So take it away, Shilpi.
Thanks, Erin. Please play the video.
Is that the end? I may have stopped it before the end, sorry.
No problem. It's all right. It's completely fine.
I think that was the end. Fantastic.
Yes.
Shilpi, do you want to give us an introduction into Prayasta and what you've been doing?
Sure. Thank you, Erin. Actually, Prayasta is a Sanskrit word. It means somebody who's trying to do good. And the motive that we started Prayasta was to do good to the in the healthcare domain, where a gap lies, and where we could amalgamate the knowledge of our materials with 3D printing. So hence we started off with Prayasta, where we rather made a technology which is a implant grade silicon 3D printer. We made it in-house from the scratch to make the end product, which is with the current focus is on breast implants and breast prosthesis for mastectomy survivors.
Fantastic. And can you tell us a little bit about why you've gone into 3D printing for these particular implants, and how you've gone about developing your own silicon that can actually be 3D printed. Because I've had a lot of experience with biology groups in the past, and what we've had to do is generally 3D print parts in acrylates and then cast the silicon out of them, because we don't actually have a widely available silicon printing process. So can you tell us a little bit how you developed that technology?
Sure, Erin. So I'll start off with why we developed this technology in the beginning itself. As you're aware that there are many 3D printers available to print different kinds of material like metal, ceramic, PLA, and etc. However, there were no implant grade silicon 3D printer available anywhere. And this polymer was never printed before, and hence Prayasta started off with this, and we had to make this technology, as I said, for the end product. It is not okay to think that one can put an implant grade silicon to any other printer to print. One has to understand its property, and hence we had to build the implant grade silicon 3D printer, or we call it IEM, which is implant grade elastomer additive manufacturing, from the scratch. So the printer is our also a patented technology. Our printer we call we call it Silimac P250. We can now print any soft tissue implant, which could be standard or personalized directly. It means that you just have to feed in the CAD file and directly print it without having to make any kind of 3D printed mold or any other mold and then cast the silicon over it. So Silimac P250 is a 3D printer developed for implant grade elastomer, specially silicon, for making personalized soft tissue implants and prostheses. It is an industrial ready machine, and it can work uninterruptedly for longer hours. It can also maintain the sterility of the printing environment and the material, producing best quality products suitable for medical application and long-term implantation. Silimac P250 can hold up to 14,000 milliliter of silicon in a single refill and is purely production scale ready. Its meticulous design maintains the sterility, as I had mentioned it earlier. And just to let you know, the build platform is 250 millimeter from all the direction. And technically on gantry level, we can go to a small, as small as 10 to 20 microns. However, the size of the nodule reduces effective resolution to around 50 microns. So this is about the technology that we have built.
Awesome. With such a big build plate, do you tend to build only one part in the build plate per build, or could you actually build multiple on the build plate at a time?
So while printing, an implant, it takes almost 6 to 8 hours depending on the size of the implant. So hence, for now we can build. For now we can print one single product or implant initially. However, the build on the bed, we can go ahead and print multiple levels or multiple products together. We just have to change the capacity of the nozzle or put multiple nozzles, and hence it can go ahead and print multiple products together if the build time is lesser than the implant, as compared to the implant currently.
I guess moving back to materials a little bit, how is the medical grade silicon different from your average off the shelf silicon that we can get from Bunnings here in Australia, a very well-known hardware store?
So medical grade silicon is the purest form of silicon that is used for healthcare application. Chemically, they are platinum based formulation manufactured in controlled environment, and then it is validated through stringent quality control and then finally certified to be used in healthcare application. So one has to understand there are 3 subcategories within the medical grade silicon as well. Just to begin with, the first one is ISO class 6, which is safe for external usage. And then there is a short-term implant, which can be used for 21 to 30 days roughly. And there are long-term implants, silicone, that are available that can go inside your body for more than 30 years. For example, like how a breast implanted that remains there in your body for almost or more than 10 years. So there are difference in various kind of silicone available in the medical grade too.
Thank you very much. Sorry, keep going.
Yeah. So, Erin, I would like to mention here as to why did we, start printing silicone to solve this kind of a problem. Is that, as I had mentioned earlier, that it should not be assumed that implant grade silicone can be, printed by any existing printer that are available off the shelf right now. And the chemistry plays an important role is vital while printing silicon. Conventional 3D printers, which are FDM or PBF or etc., either use filament or powdered form of material. Natural form of implant grade silicon is liquid of high viscosity and cannot be converted into filament or powder. Hence, conventional 3D printer cannot use implant grade silicon. Then implant grade silicon has two components. One is a base polymer and a cross-linker. When both are mixed, a cross-linking reaction actually starts happening, and which is very quick or instant. And hence the mixture turns into a cured form after a certain interval of time. This is the only time that is allowed to print. Otherwise, it will get permanently cured, and hence conventional 3D printers are not usable. Then other 3D printing techniques like SLA, DLP use UV or other light-based material methods to cure the liquid materials, and hence exploit photocurability nature of materials. Implant grade silicone are not photocurable and cannot be printed by these techniques either. And hence, also important thing is that you can also get those syringes to make any kind of use implant grade silicone for, but it can only use or make smaller structure. It cannot make something which is bigger in size, and because it will start curing inside the syringe again, so you will have to only end up making a smaller structure. And hence we had to build this technology because we didn't want to wait. Ours is a real time curing, so we didn't want to wait for one layer to fall and then wait and then again another layer to fall. So what happens is it may just start falling apart, the entire structure. So we thought of making something which is real-time curing.
Awesome. Thank you so much, Shilpi. Because of time, again, I'm going to move on to the metals section, but thank you so much. And anyone who's looking into implant grade silicon or tissue sort of implants, definitely get in contact with Shilpi because they've done some amazing work and have some trials that are starting soon, which is really interesting to hear about. There's a question that just popped up, but I will ask it at the end once we've made sure Trish and Dina have some time to answer questions. If we don't get back to the question, make sure you catch up with Shilpi after the panel. Fantastic. So next we'll move on to Trish Pollock, who is from AML 3D, and they specialize in wire arc additive manufacturing. Trish, would you like to give a little bit of an introduction into wire arc and AML 3D?
Yeah, sure. Hi, everybody. Thanks for joining us this afternoon. So Erin's actually got some videos that she can share with you in the presentation. So at AML 3D, we specialise in wire arc additive manufacturing for large parts or for parts using exotic materials. So think your invars, your titaniums, super duplex, and so forth. So we've recently come off a massive year where we printed the largest shipboard fitting, and you're looking at the largest additive manufactured verified high pressure part for oil and gas at the moment. So this particular piece was printed out of it's 940 kilos, and it was printed out of a carbon steel comparative material, a wire feedstock, and it was certified by Lloyd's Register. And part of that certification is that it was hydrostatically tested to withstand 790 kPa. So that's quite a significant amount of pressure. So to do this, we use wire feedstock, we use welding science, and we pair that with our patented wire additive manufacturing process. And we've got some proprietary software behind the scenes that that supports the process as well. So if you can flip to the next video, please, Erin. And then, so this particular piece, this is a prototype we had made that's very similar to the Keppel Panama chalk that we printed. So this is the largest shipboard fitting that has been printed globally. The Keppel piece that was verified by D&V is 1.7 meters by 1.1 by half a meter in depth. It is 1.4 tons. So this thing is, it's massive. It's quite impressive part. It was proof load tested to 20% higher than its designed working load. So 20% stronger than its intended use. And that was printed out of ER70. So sometimes we get asked how is it that we end up with the stronger material properties, and it has to do with the materials that we use and the interpass process. So we can control the heating and cooling of the material as we go along. So if a part requires forced cooling, we can do that. But if a part requires, generally they just require cooling as they go around and in their printing process. So it's pretty exciting what we do. So these are some examples of the big additive manufacturing products that we can do. If you can share us the next slide. So this particular piece is a propeller or side thruster that I had our team do for R&D purposes. I wanted to learn a little bit more about the material waste savings. So we embarked on a stainless steel project. So typically this 22 kilo finished product propeller would be billet machined. I do apologize, it's billet machined. From a 460 kilo billet. Our material deposition is 50 kilos in total. So by the time you do the maths, you're looking at a 95% material waste saving, and you're also looking at a considerably lower build time. So to machine a 960 kilo billet to a 22 kilo part, you're looking at 97 hours of machine time alone. For us, we're looking at, in our wire additive manufacturing process, you're looking at 23 hours of arc and machine time in total. So it's considerably less. So when you're talking about materials for additive manufacturing wire feedstock, you're not just talking about the material strength properties, you're also talking about material waste savings. And obviously that leads on to lowering carbon footprints of manufacturing processes, because while, yes, there is some energy input and output into making wire feedstock, when you're looking at the actual manufacturing process of the part, the less machine time, the lower need to have energy input to create a cast, to create the tooling and whatnot that you often see with conventional manufacturing. You've got incredible carbon footprint savings. So yeah, it's pretty exciting.
Yeah, that's absolutely amazing, because I know we always talk about additive manufacturing in that it is sustainable and it is way better in all these reasons. And I know for other people who've worked in it for a while, you start to realize, hey, this process isn't actually as environmentally sustainable as we thought to start with. However, when you start to look at massive pieces like you're doing at AML 3D, it's very, very interesting to hear that, yes, okay, you get that massive material saving compared to machining something out of a billet, but also the build time is so much less than machining it from a billet as well. Usually we think of additive as generally a slow process because you're doing it layer by layer and you have to build up the material. But the fact that you can save so much time as well on your parts is absolutely phenomenal and fantastic and really exciting, I guess, for industrial applications of AM going forward.
Most
I
certainly.
guess my next question, or my main materials focused question for you, Trish, is what alloys have you used most so far, and what alloys do you use overall in general? What's the most exciting out there alloy that you've used before as well?
Okay, if you can share us with the next slide. So I actually have a image that I've provided that that showcases some of the materials that we do use. So we can print with a range of wire feedstocks. So they're obviously synergistic lines with welding, CMT, PMT lines. We can, it's a range of aluminium, titanium, nickel, and steels. So obviously we cover off the mild, the stainless, the martensitic, the austensitic. We also do duplexes and super duplexes, and we can clad. We do the exotics. So I think the most exciting thing that we've happening is a titanium piece for a company in the US. And we're also working with a local company around an aluminium product, which I'd love to talk more about, but it's for aerospace. And, you know, it's super exciting in terms of the application of some of these materials. So yes, to go back to your question, nickel, aluminium, bronze is probably one of our common alloys as well. So when you're talking maritime, for example, marine, like we can do propellers and we can do single blade propellers, so you don't need to, you know, remove a propeller completely on a large vessel. You can just go in and replace the single blade. When we're talking high pressure parts, you know, there are a range of hostile environments that high pressure parts operate in, and so obviously we can match the material to suit the environment, whether that's a highly corrosive environment or whether it's an environment that requires a low expansion, low thermal expansion. So obviously that means that the part can't be enabled to expand too far because it might not be suitable, or it might cause a failure down the track. So yeah, there's even, you know, materials that have lower sparking properties. So if you've, yeah, it's intense, the type of stuff that we can use and we can apply to industry. I don't think there's just enough time for me to be able to share it with everybody. So yeah,
I'm sure you would love to go on and talk about all of the different applications, and particularly, like, you guys have worked in energy and oil and gas and maritime, and those industries have such difficult environments to have metals in that still retain their structural strength without corroding away in a week. So yeah, there's some really exciting applications and materials that you're obviously developing for those specific applications as well. And yeah, it'll be really exciting to see what AML 3D does next. So
yeah, and look, we do have some exciting things that are happening. So we've got our partnership with Deakin University and their Institute for Frontier Materials. So we're working with them to develop aluminium scandium wire feedstock. So you know, that has potential applications in aerospace. So think things like rockets and whatnot. So you went by introducing an alloy like scandium, you're improving the material properties and the weldability of aluminium, because it can be quite a fickle material to work with. Soft.
I think that's actually a fantastic segue into Dina's work, if you don't mind, Trish. Just because, again, we're running short on time, because Dina has been actually working on developing aluminium alloys specifically for laser powder bed fusion. And she's just going to talk a little bit about the alloys that she's worked with and what she's done at MCAM. And also one of the questions that popped up in the QA that you might as well be able to answer, Dina, is that for the 5000 aluminium series, how do you control loss of elements? So I assume that's evaporation of lower melting temperature constituents and things like that from your alloy. I'm not sure if you can talk to that as well as part of your aluminium alloy design background. So I'll give you the floor.
Thanks, Erin. So let me introduce first what I'm doing, then we take the question. So in Monash Center for Additive Manufacturing, it's a research platform under Monash, and we are focusing actually on metallic materials. Mainly we develop these metals for aerospace applications, but also we are serving other industries such as nuclear energy and biomedical. So our research for the moment is actually developing lightweight alloys such as titanium, magnesium, aluminium. We also have research on nickel, super alloys, steel, high entropy alloys. For me, I'm focusing on laser powder bed fusion, and we are developing high strength aluminium reinforced with scandium and zirconium for aerospace application. As a matter of technology in MCAM, we can use also DAD, direct energy deposition. So to give you just a brief idea about the technology, can you run the video, please? So this is from one of my builds. So any intricate geometric part we can actually model by a CAD file, and then we send the file to the 3D printer. High power laser beam will hit the powder and will selectively melt the powder guided by the CAD file. Then the build platform in the middle will descend by one layer thickness, and then the process will keep on repeating until the 3D part is completely fabricated. So in comparison with DAD, we can achieve actually better dimensional accuracy and better surface finishing for laser powder bed fusion. However, as you can see, this is the platform of a commercial EOS M290 machine. We are limited by the size of the platform. So actually the platform here in the image is 25 centimeter by 25 with a depth of 30 centimeters only. So I think in comparison with DAD and WAM, we are limited by smaller size for the part. So usually the first stage when we developed an alloy for additive manufacturing is the process optimization. In simple words, we are trying to determine the set of processing parameters that we should use in order to achieve defect-free parts. And we use different techniques. We will not go into the details, but one of the simple techniques, we build small cubes and then we go for microstructure characterization in order to investigate the porosity level. Once we can achieve a density beyond 99.5, then we can determine our processing window. We also have to optimize the post-processing heat treatment because as you know, we are using extremely rapid cooling. It can reach up to 1 million Kelvin per second in LPBF technology. So residual stresses will develop in the part. That's why the post-processing heat treatment is very important to relieve the residual stresses. And in case of some age-hardened alloys, also we are strengthening the alloy. So once we determine the processing window, we move into a mechanical property investigation in order to confirm the structural integrity of the part at room temperature and at elevated temperature. And then we go to a microstructure characterization in order to build our understanding of how this new process compared to conventional techniques is actually affecting the microstructure, because this helps us in further upgrading different classes of alloys. So for the magnesium-rich alloys, such for example, scalmalloy, that is the question, we we can't avoid the evaporation of some low melting temperature elements such as magnesium. Maybe by controlling the processing parameters, we can limit the energy density in order to avoid extreme evaporation. So we stick to the minimum energy density that can achieve a good consolidation. We don't need to exceed that in order to avoid the evaporation, but we found that we cannot. That's why in our case, we developed a manganese-rich alloy compared to the magnesium-rich alloy. And we control the magnesium to be less than 1.5% in order to avoid the evaporation, because when the evaporation takes place, you end up with oxide inclusions in the material. You also might have some pores. So you cannot avoid this 100% to answer the question.
Sounds like you can mitigate it quite well, though, by changing the chemistry of that alloy and swapping out some of those lighter melting temperature elements and putting in higher melting point ones. In my PhD work, I was working with titanium, but also tantalum. And tantalum is a really refractory metal that does not melt very easily. So we had to use very, very, very high energy densities to try and get the tantalum to melt without the titanium evaporating, because the melting temperature for tantalum is actually just a few degrees higher than the evaporation temperature for titanium. So getting them molten at the same time is quite difficult. But yeah, as Dina mentioned, there's a little bit you can do with processing parameters as well as alloy control. One of the other questions in the Q&A, Dina, that I think goes well to in your topic, and what is your recommendation for metal powder producers to focus on considering the powder demand for AM? I assume it's asking what particular alloy classes that powder producers should focus on, considering the powder bed fusion industry out there at the moment.
So we are actually, there's some limited metallic materials that can be reliably processed by LPBF. What we are doing in MCAM, and also this is the trend in industry and in academia, is that they are trying to increase the variety of powder that can be actually printable by additive manufacturing in general and LPBF in particular. So for example, in MCAM, we are actually developing some conventional alloys, such as aluminum, silicon, casting alloys, wrought alloys. These were used by conventional techniques, and we are trying to work out their printability. However, we are doing great effort in developing new recipes specifically for additive manufacturing that is not just can mitigate the the cracking due to the rapid cooling. We are actually using the rapid cooling on our side in order to foster the strengthening mechanism in the alloy. So this is what I'm recommending: more research and developing alloy compositions in any type of alloy system, specifically for additive manufacturing. So we don't struggle. We want to use this rapid cooling on our side to make stronger and more high performance alloys.
So our recommendation to powder producers to keep an ear to the ground for the newly developed alloys and stop relying on the ones that exist already for conventional manufacture, because we will be able to do much more exciting things once we have specific alloys developed for metal additive manufacturing.
Exactly.
Thanks very much, Dina. I think we've got about 2 minutes left, and there's just a question that's popped up in the Q&A that I'd love to ask Shilpi while she's here. The question is, are there any concerns regarding the surface roughness of implants? Apparently there's been some recent media coverage about cancer related to textured surfaces of implants. Can you talk to that at all?
Sure, Erin. I was actually answering that question.
I thought you might have been, but I thought since we're here, we may as well say it.
So I would like to tell you here that we have our own patented technology called the novel internal architecture, which is a gamut of architecture. It's not limited to one design. If you can see this is the wall and voids that we use. These can be customized to any kind of walls and voids, which gives another kind of a implant surface. It's not either textured or smooth. So hence, likewise, we can also print any other soft tissue implant. This is a chin implant that I'm talking about. And I would like to really talk to this. I don't know the name of the person, though it's not visible here. But yes, I would like to go in details with this person, whoever asked me this question. and talk about more on the novel internal architecture and how do we use it for making the implant. Yes, we understand this is the the off-the-shelf implant that you get, which is a balloon structure filled with silicone or gel. Ours is completely liquidless, but it gives you that soft texture because of the novel internal architecture.
Which I think also is a really good point, that it completely takes away the risk of burst, which you hear terrible stories about with breast implants. So having that internal architecture is very interesting and very beneficial for the patient as well. I think I'll have to end it there because we have reached our final time. But thank you so much to everyone in the panel. You guys have been fantastic and very helpful at answering all the questions that have come up. I wish you all the best for all of your industry applications and developments over the next couple of years, and looking forward to talking to you at the next conference and hearing what new exciting things have been developed. So thank you so much. And I will ask, I think, Eve to take back over control of the stage and move on to, actually, no, we're at the last presentation, actually. So we're going to head back into the networking. If you want to chat with someone that you've heard talking in the panel today, I'm sure they'll stick around to talk about their different work in the different industries. So thank you very much. And Eve, I think that's it.
Yep. Okay, so if anyone wants, you can
Erin.
go back to the main stage and you can go for networking sessions with others that you would like to talk to. So it'll be easier. Or you can just go to the chat and you can search for the participant and chat with them directly. So it'll be easier. Okay?
Awesome. Thank you so much.
Thank you so much.
Thank you.
Thank
Thank
you.
you.
Bye, everyone.
Bye.
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 Bye.